Welcome to the Electrical Grid Testing and Commissioning Training, Module 3, focusing on voltage transformers. This module is designed to deepen your understanding of voltage transformers and their critical role in the electrical grid. Let's get started with this essential part of our training for 2026. Here, we have the reference framework that supports the testing and commissioning of electrical grids. This slide highlights key standard organizations that provide guidelines and standards widely used in our commissioning manuals and test scripts. The most important references include the IEC, which is the International Electrotechnical Commission, and the IEEE, the Institute of Electrical and Electronics Engineers. Both provide crucial standards for electrical systems. Other significant bodies include ASTM, known for materials testing standards, NEMA, which focuses on electrical manufacturers, and ANSI, which oversees national standards. We also rely on organizations like SIGER for large electric systems, ICA for insulated cable engineering, and KEMA, which acts as a verification body for electrical engineering materials. When there are discrepancies between project specifications, manufacturer instructions, and standards, we always apply the most stringent approved requirement. It's essential to document the specific reference used on each test sheet, ensuring clear traceability for future reviews and audits. Here we have the voltage transformer turns ratio schematic, which is fundamental for testing and commissioning in the electrical grid. This schematic acts as a key reference to verify the primary to secondary ratio, ensuring accuracy and proper functioning. Using specialized test equipment like the CPC 100, we can measure the turns ratio and check for any deviation, which helps maintain system reliability and safety. This process is detailed in Commissioning Manual number 3-1, guiding us through the verification steps systematically. Let's walk through the voltage transformer turns ratio test procedure, which is crucial for testing and commissioning the electrical grid. This test verifies the actual primary to secondary voltage ratio, polarity convention, burden isolation, and ensures proper test card documentation. We start by confirming the VT tag, location, voltage ratings, phase identification, terminal markings, and referencing the approved drawings. Safety is paramount, so we must verify that the VT is de-energized, isolated from live circuits, and that burden wiring and fuses are properly managed according to the approved procedures. Next, position the test instrument on a stable, dry surface, apply protective grounding, and connect the leads exactly as per the schematic and terminal box instructions. Selecting the correct test card is essential. Enter the nameplate ratio, expected secondary voltage, frequency, and any necessary correction settings. Begin the test at the approved voltage and carefully monitor for abnormal noises, unstable readings, unsafe conditions, or warning indicators. Record all key measurements, including primary and secondary voltages, calculated ratio, deviation percentage, phase angle, polarity, and tap details. This process is repeated for every phase, tap, and configuration specified by the approved test plan, saving or printing each test card. Once testing is complete, restore burden wiring, fuses, terminal covers, and grounding status under approved instructions. To meet acceptance criteria, ratio deviation, phase angle, and polarity must align with manufacturer and project standards. All readings should be stable, consistent across phases, and free from alarms, damage, or discrepancies. Finally, the result package includes the VT ratio result table, test card exports, photos of the nameplate and terminal box, isolation and restoration records, instrument certificates, and a witness signature. The hold point requires the witness to verify burden isolation, terminal restoration, and correct ratio and tap selection before returning the VT circuit to service. This ensures safety and accuracy before energizing the system again. Here we have the schematic for insulation testing of voltage transformers, an essential step during the testing and commissioning of the electrical grid. This diagram provides a clear reference for conducting insulation tests between the primary winding and ground, the primary and secondary windings, and the secondary winding to ground. These tests are crucial to ensure the integrity and safety of the transformer before it goes into operation. By following this schematic, we can accurately verify the transformer's insulation condition and prevent potential failures in the field. On this slide, we focus on the insulation testing procedure for voltage transformers as part of electrical grid commissioning. First, it's critical to verify insulation for the primary, secondary, and ground boundaries before any functional testing begins. We follow a detailed reference procedure, WING 6460-002-024-025, using the VT nameplate, terminal box diagrams, and approved isolation plans. The required equipment includes a calibrated insulation resistance tester like a Megger or an approved CPC 100 function, along with discharge leads, test leads, barriers, tags, personal protective equipment, and test documentation. The testing process involves several steps. Confirm the VT's identification and approvals, ensure it is de-energized and isolated, then measure insulation resistance between primary to ground, primary to secondary, and secondary to ground by applying approved DC test voltages for specified durations. It's essential to allow readings to stabilize, discharge after each test, and never leave terminals charged. All test details, voltage, duration, measured resistance, ambient conditions, phase, and terminal boundary, must be recorded precisely. After testing, restore terminals, fuses, covers, and grounding according to switching instructions. Acceptance requires meeting approved insulation resistance thresholds without flashover or abnormalities. The evidence package includes all test results, photos, calibration certificates, witness signatures, and punch list closures. Finally, a hold point ensures a witness confirms safe isolation, correct connections, complete discharge, and restored conditions before signing off. This guarantees safety and compliance before moving forward. Here we have the winding resistance schematic for the voltage transformer, which is crucial during the testing and commissioning phase of the electrical grid. This schematic serves as a clear reference to guide the measurement of winding resistance. It's important to follow this carefully to ensure accurate readings and, above all, to maintain safe disconnection control throughout the process. Adhering to this schematic helps prevent faults and ensures the transformer operates reliably within the grid. Let's go through the voltage transformer winding resistance test script carefully. This test is critical for verifying the resistance of the transformer windings by phase and terminal path, using safe current injection and ensuring proper restoration afterwards. First, we reference the relevant documents like WING 6460-002-024-025 and always use the VT nameplate, winding connection diagram, approved terminal plan, and test card settings. The main instrument used is the Omicron CPC 100 or a comparable low-resistance test set, along with Kelvin leads, grounding lead, terminal tools, personal protective equipment, and necessary test forms. The step-by-step procedure starts by confirming the VT tag, winding designation, phase identity, terminal markings, and temperature requirements. Next, we verify the VT isolation, discharge conditions, safety boundaries, and burden or secondary terminal management. Then, the instrument is grounded and current and voltage leads are connected exactly as per the schematic. We select the winding resistance test card, enter the current, winding ID, and temperature, and start the measurement, allowing the value to stabilize before recording. This process is repeated for each phase, winding, tap, or terminal pair as required. We record the raw resistance, corrected values if needed, temperature, test current, phase, and instrument serial number. Before disconnecting, we stop the current output, discharge if necessary, and restore all terminal connections. The acceptance criteria require that resistance values be stable, comparable phase to phase, and within approved manufacturer or project tolerances. There must be no open circuits, abnormal heating, loose terminals, or unexplained deviations. Finally, the result package includes the winding resistance table, saved test card output, temperature records, terminal photos, instrument certificates, deviation analysis, and witness signature. The hold point ensures the witness verifies the output is off before leads are removed, and that all wiring is restored to its as-left condition. This careful process guarantees accuracy and safety in the commissioning of the electrical grid. Here we have the voltage transformer voltage withstand schematic, which is crucial for testing and commissioning the electrical grid. This schematic serves as a detailed reference for verifying the voltage withstand capacity and ensuring high-voltage safety control. Following this ensures that all components can handle the expected voltage levels without failure, maintaining the reliability and safety of the grid. This information is drawn from Commissioning Manual number 3-4, which provides standardized procedures and guidelines for these critical checks. This slide outlines the voltage transformer voltage withstand test script, a critical part of testing and commissioning electrical grids. The key purpose here is the dielectric withstand verification for the selected VT insulation boundary under controlled high-voltage conditions. We follow this procedure as per the reference WI NG 6460-002, which includes using the approved voltage withstand limit, the VT schematic, test card settings, and safety method statement. For equipment, we use the Omicron CPC 100 or another approved test set along with high-voltage leads, grounding tools, barriers, warning signs, PP, and appropriate documentation. The test itself involves several important steps. First, we confirm the VT identification, ratings, and the test parameters. Then we establish a safe work zone with all necessary precautions and verify the VT is isolated and safely disconnected from sensitive secondary circuits. We properly ground the test set and connect leads as per the schematic. Next, we select the correct test card, apply the test voltage carefully while monitoring for any leakage or abnormal signs, and record all results meticulously. After the test, it's crucial to discharge the system safely and restore wiring only following approved instructions. The acceptance criteria here is that the VT withstands the approved voltage without breakdown, flashover, or insulation damage, and that all discharge and restoration procedures are fully completed. The evidence package includes test results, safety checklists, photos, certificates, and witness approvals. Lastly, there is a hold point, meaning the client or commissioning witness must approve before we energize the HV output and proceed with final restoration. This ensures safety and compliance throughout the testing process. Here we have the voltage transformer polarity check schematic, which is crucial for ensuring the correct operation of our electrical grid. This schematic provides a clear reference for verifying polarity and interpreting CPOL or test card results. Understanding and correctly applying this schematic during testing and commissioning helps prevent potential faults and ensures reliable system performance. This is all detailed in Commissioning Manual number 3-5. Before connecting voltage transformers to relay or metering circuits, it's crucial to verify the VT terminal polarity, secondary direction, and phase relationship. This ensures accurate and safe operation. We follow the approved procedure outlined in WI NG 6460-002, using the specified VT terminal diagram, polarity markings, and wiring diagrams as our guide. The key instrument set includes the Omicron CPC 100 or an equivalent polarity test set, along with approved probes, test leads, grounding leads, terminal tools, and proper PP. The step-by-step script begins by confirming the VT's tags, phases, and markings, followed by verifying that the VT is isolated and safe for testing. Next, we ground the test instrument and connect the polarity leads exactly as per the schematic. We select the POL-check test card, configure the output range and test settings, then apply the test signal. A green indication confirms correct polarity, while red indicates a problem like reversed or distorted polarity. We carefully record results for each phase and terminal, then repeat the process for all taps and secondary windings as required. Once testing is complete, we restore the wiring and connections, confirming the secondary circuit is ready for operation. The acceptance criteria are that all terminals must match the approved polarity conventions. Any issues must be corrected and retested before final sign-off. For documentation, we compile a comprehensive evidence package including the polarity checklist, test card exports, terminal photos, phase tables, any corrections, instrument certificates, and witness signatures. Finally, a hold point requires a witness to confirm every phase's polarity results and verify the secondary restoration before the VT is released for use in protection and metering circuits. This meticulous process ensures accuracy and reliability in our electrical grid commissioning.